Hi, and welcome to Gravitational Fields Lesson 6b. So the question I asked you was to draw both the potential and kinetic energies as a function of distance from the surface of the planet. Let's start with the potential energy, because this is a graph you've drawn already. We already know at infinity it's 0, and then it's just going to get more and more and more negative as we approach the surface of the planet. So this is a graph we've already seen. That's going to be the case of the satellite or any object. It's simple. The kinetic energy, there's two different ways we can think about it. The first is we can say, well, we know it's going at its fastest just before it hits the planet. So therefore we'd expect a max at this is r. We're then going to expect it to change as it goes towards infinity. Let us consider a satellite infinitely far away. Well, at that point there's no force on it, so it's probably not going to be moving much. So it's going to have 0 kinetic energy. So now what we've got to do is get from this point to this point. And as normal, we're going to ask what shape is it. Now we could figure it out mathematically, but there's a little trick we can use, which is conservation of energy. We know the total energy of the satellite must remain the same. And if it has 0 energy at infinity, it must overall have 0 energy when we reach the surface of the planet. So the two halves of the graph are going to mirror each other, which is why potential energy has to be negative, so that a positive kinetic energy can still result in conservation of energy. It would only work if we define potential negatively, like this. That's the only way you can get overall the energy remaining constant. Neat, eh? So, what does this graph tell us? Well, firstly, because our speed is going to be equal to half mv squared, and our potential energy at any point is going to equal the field times the mass, our speed is actually going to be independent of mass. The m's are going to cancel, which means that our speed can actually be displayed as a function of our distance from the planet. Any satellite which is orbiting the planet at a given distance will have a set speed. This leads us to two really neat things. The first is geostationary orbit. So geostationary orbit just means that the satellite is always overhead, and it takes 24 hours to go all the way around the Earth, so that it's moving at the same speed as the Earth is. Now it turns out this only works if you're over the equator. Because the Earth isn't fully circular, it's a bit sort of, it gets a bit wider at the middle and bulges a little. Yeah, you can only do geostationary over the equator, but that's still really, really useful, because it means if you want, like a telephone mast, to always be beaming to the same satellite, having it in the same position over the Earth as it rotates is obviously very helpful. But we already know that a given speed is going to be set at a given height. So therefore, every geostationary satellite is exactly the same distance from the Earth, meaning there's actually only a very finite number of geostationary satellites you can have, because they've all got to be the same distance from Earth, and they're all above the equator. So we're actually running out of space to put geostationary satellites in. There's only so many you can have, which is really neat. The second thing this tells us about is something called Keplers Third Law. This is something that a cat called Kepler worked out. He was a monk just before Newton who wrote down lots and lots of stuff, and he had some laws about how the planets were moving around the sun. He noticed that when a planet is closer to the sun, it goes faster. When it's further away, it goes slower. Lots of planets, it turns out, don't just go around in a circle, they go around in a kind of oval shape, like this. And what he noticed was they went faster when they were close to the sun and slower when they were over here. Which again would make sense. We know that over here it's going to have more gravitational potential energy because it's further from the sun, and here it's going to have more kinetic energy because overall the energy is going to be 0, so therefore if it loses one it gains the other. It's going to speed up when it gets near the sun. This is what Kepler worked out, which was really clever. If you take a certain amount of time, let's say a week, and you mark where the planet is a week apart, and then you draw an arc with the sun at its centre, and then you do it again when the planet's closer, and in a week it's obviously going to move much further because it's going faster, and you draw out an arc. If you then look at the area of the two arcs, they'll be the same. So a planet going around the sun sweeps out an equal area in every unit time because it speeds up when it gets closer. Isn't that great? There's some questions underneath. Have a good weekend. I'll see you next week.